when we ask coq what the type of this definition or this expression is, it's going to tell us it has the type nat arrow prop. That is, give me a nap, and I will give you a statement or a proposition. So, let me stop that. Right, so in coq, if we have a function of this flavor that takes some arguments and returns a proposition that defines properties of that, or returns a proposition, we say it defines properties of those arguments, right? So, for instance, here is a polymorphic property of injectivity. This is a concept that we saw in the previous lecture when we were talking about inductive data type definitions and their constructors. But we can make an assertion about any sort of function. So here, the injective proposition has two type arguments, and it takes a function from the first type to the second, and says that for all arguments, if f of x equals f of y, then then x equals y, right? And now we can reuse this property to make an assertion about a particular function. In this case, the constructor, the successor constructor. We can reuse this definition in it and then write the proof as we would expect. Okay. So again, every statement, every sort of mathematical fact you can insert in coq has the type prop. So equality, the equality operation that we've seen previously also returns a prop. So the expression n equals m, as it says here, is just a syntactic trigger for a particular definition, EQ, which returns a property on the two arguments that you pass it, right? Of course, as we note here, because EQ can be applied to any type, it's polymorphic in the type of the arguments. So if we check the type of EQ, we'll see it takes a type, it takes two arguments of that type, and it returns a proposition, a statement about those particular arguments. Okay. Here's the interactive part. I will ask you, what is the type of the following expression? Think about it, and I guess raise your hand when you're done. Okay, someone shout it out. The type of the following expression is, oh, 1, yeah, sorry. It's like, give the number, yes, thank you. Yeah, that sounds right to me. Okay, what is the type of this expression? Think about it. 2. Is it? It's, okay, so I have, who thinks it's 1? Okay, that 1 is correct. Okay, so why isn't this 2? So, yeah, this is a little bit tricky. And yeah, we'll get to that point in a second. So this is a proposition. So this is just a mathematical statement. So this for all is just one way we have of building up propositions, right? So this is, it's just a statement, so it has type prop. What is the type of this expression? One, right. Exactly right, because again, this is just some assertion. It turns out that this is a not true assertion, because if n is 0, this won't hold, right? So this won't hold for all n. But again, we don't care about truth, we're just caring about assertions. Okay, what is the type of this expression? Think about it. 4. The statement is 4. Okay. Why is this not typable? Why does this make sense? Well, think of it this way. This for all quantifier quantifies over some argument, and it's followed by a proposition, right? So, oh, okay. So the expression that follows the for all quantifier, what type does it have? Nat, right. So you can't, the for all quantifier expects to be followed by a proposition. It's followed by something of type nat. It thus doesn't type check. Coq will throw a typing error. Here we go. What is the type of this expression? Nat to nat. Yes, 3. Exactly right. Because it takes an argument of type nat and returns a natural number. What about this expression? 2, exactly right. So here is an example of an expression that takes a natural number and gives you a proposition, as opposed to that for all statement, which was itself just a proposition. Okay. Oh, here's a good one. Which of the following is not a proposition? So which of the following expressions, if you checked it in coq, would not give you a prop back as the type? 3. Yes, exactly right. What is the type of that expression? Bool, exactly right. Yep. Okay. Okay, so again, just to recap, propositions are simply the type that are assigned to statements of mathematical facts. And again, these are first-class objects, so in coq. So yes.
So is the type prop inductively defined? If so, what are its controls?
No, it is not inductively defined.
Can I
So
define my own prop?
yes. And in fact, we will see how to define your own inhabitants of prop tomorrow morning. But the way to think of this right now is that just as type is sort of the uber type for many things, prop is the uber type for propositions. Okay. And just as you can introduce your own types using the inductive keyword, you can introduce your own propositions in a way that we'll see tomorrow morning. I don't want to give it away. But before we, yes?
So if I have a free variable, it's not quantified, does that count as a prop? Like x plus 5 equals 7?
If you just had the expression x plus 5 equals 7. Now, assuming that x had not been defined previously, it hasn't been assigned a definition, coq will throw an error because you're not allowed to have an open expression like that.
Okay, so I can't get a free variable in coq like that. And assigned, it's not.
It is not a well-formed expression.
It's not well-formed.
Yes. Every variable needs to be bound by a quantifier or be attached to some definition. It's a good rule of thumb. Yeah.
So if type is the type of types and prop is the corresponding one, why do we have this distinction? Why don't we have propositions as types?
So you're asking what is the distinction between prop and type?
Why are we making this distinction?
So the reason for this, I don't want to get into too much detail, but the intuition is that props are referred to proofs, and these things aren't computationally relevant. And at a high level, what this means is when we use coq's extraction mechanism to produce equivalent OCaml expressions, everything that lives in type will actually produce an OCaml definition, and things that live in prop will get erased. And there are other deeper reasons for this, but
So it's not just a practical erasure annotation. So if I wanted to have propositions as types, I could just interpret my types as propositions, but not as prop, and then they would be computationally relevant when we extract an algorithm.
I think the short answer to that is yes.
Make sure to repeat questions for them.
Oh, thank you. So let me see if I can repeat your question. Your question was, could we also define similar statements and assign them type and have them be computationally relevant and get extracted? Was that the question? And the answer is yes. You can do that. But indeed, part of the reason for using prop is as a signal that you don't want this to be extracted. It is not important. It is a mathematical statement, something that doesn't live, it does not represent a function or a term that you want to be computed. I think it's the right intuition. Any other questions? I like questions. Nope. Yep.
So basically, props are those so data is those to props.
So yes.
Expression of type prop. We can do a proof for that.
Yes. So the question was, do expressions of type prop? When we want to write a proof, we have an expression of type prop, and we write a proof for it to show that it's true, and that is exactly right. So when we define a theorem, we make a statement. The statement has type prop, and the proof script we write generates evidence that that assertion is true or statement is true. Yep. Okay. So if there are no more questions, now we're going to look at how to, so far, like I said on the first slide, we've only seen 3 ways of building up props. We have for all quantification, we have arrows for implication, and we had equalities. So now we're going to see how we can build up propositions, larger propositions, using a variety of logical connectives that should hopefully look familiar to you. The first of these is, of course, conjunction. So conjunction or logical AND is something that people may have seen before, probably have seen before. And this is just a way of asserting that facts, propositions A and proposition B are both true. And we write this using the logical AND connective, which looks like a little wedge. So as an example, here is, we're asserting that both 3 plus 4 equals 7 and 2 times 2 equals 4. So let me switch over to my proof buffer here. Oops. And make sure that this is readable for folks in the back. This is an example. So before, we had a couple of tactics that allowed us to solve goals of the form, x equals y. Right, we had this reflexivity tactic. And correspondingly, there's a tactic that lets us solve goals of the form, or make progress, I should say, on goals of the form A and B. And in particular, the tactic we use for logical AND is called the split tactic. So just off the top of your head, if you want to prove A and B, what do you need to prove?
A and B.
Right, you need to prove A, and you need to prove B. And that is precisely what the split tactic does. I mean, it follows this intuition precisely. So here we go. Oops, let me bump up the size here. Hopefully. There we go. So when we use split, we're going to get 2 subgoals. So this works on, for right now, we can just imagine this works in goals of the type A and B, and we call split, and we get 2 new subgoals, proving the left conjunct and proving the right conjunct. And of course, once we've done that, we can apply the tactic that we have in hand for dealing with goals that look like equalities. So reflexivity solves this goal, and reflexivity solves the next goal, as you might expect. Similarly, this pattern of using split works for any proposition. So if we want to prove, we can write a proof that sort of exhibits this fact that for any A and B, if we can show A and we can show B, then we can show A and B in just the way that you would probably expect. Okay. All this slide is saying is that this AND intro lemma that we proved before has the same effect as using split. It's going to generate 2 subgoals, 1 for each of these assumptions of this proof of the AND intro proof. So if we apply AND intro, we're going to end up in the exact same proof state with the same subgoals that we had when we used split. Yes, I'm going to skip over the next one because we're running a little bit behind because of our AV issues. Okay, so this is how you reason about goals or manipulate goals which have a conjunct in them. What if we have some conjuncts as a set of hypotheses? What if, for instance, we know that n equals 0 and m equals 0, and we're trying to prove that n plus m equals 0? Okay, so this is how do we, whereas before we were sort of working backwards from the goal, here if we have some and fact and we want to work forward from that, how do we do it? Well, the solution is to use the destruct tactic. So in much the same way that we could, well, I want to say that. So here we can do intros, and now H has type n equals 0 and m equals 0. And when we destruct H, what do we get? Well, we get 2 new assumptions, namely the left conjunct and the right conjunct. This as statement here works just as we saw before with the destruct. It gives names to each of the assumptions that we're introducing to the goal, or into the proof. And now, once we have these in hand, we can actually rewrite with hn and rewrite with hm. And now we have 0 equals 0, and we're done. So okay, so why did we have to do that? Well, imagine we tried to, oh, nope, I'm not going to go up. I'm not going to do that. Okay. Not going to go overboard. Okay. One thing to note is that it says as usual here. I'm not sure if we saw this in the previous lectures, but we can actually destruct these ands right when we introduce them. So by using this bracket pattern matching syntax here, it's going to intros n and m, and the brackets mean intros this as h, and then immediately call destruct as using these two names. Yeah. Can we invert the prop instead of destructing? Sorry, the question was, can we invert the assumption instead of destructing? And the answer is yes, it works in this case. Yes, that's all I'll say about that. Okay, so. Right, so you might have noticed on that this idea, why would we ever end up with ands in the, why would we ever end up with an assumption that has this and form, right? Because as we saw, this is isomorphic to just making two assumptions, right? We can just assume n equals 0 and m equals 0. So why would we ever end up with a goal state that looks like this? Well, for the present example, both things work, but sometimes when you're working on a goal, you might want to assert some intermediate proposition or statement and prove it and then use it. So as an example, let's here we go. So as an example here, when we're trying to prove this goal, we're trying to show that n times m equals 0, assuming that n plus m equals 0. The natural way to prove this is to first show that n equals 0 and m equals 0. And we can do that by asserting this intermediate goal. We saw this tactic a little bit earlier. Now we have to prove this goal, which follows straightforwardly from some other sublemma that we've used previously. And after we prove it, we have this assumption in hand, but now we have an and we need some way of working with it. So we'll use destruct and proceed as before. There are other cases where and will crop up in an assumption, and we'll see one of those actually a little bit later in this lecture. Okay, and just as an aside, this little wedge operator is actually syntactic sugar for so A and AB, in much the same way as the equality symbol is actually syntactic sugar for this an EQ identifier. So what is the type of and? Well, if we check it, it's going to take a prop and another prop representing the two sides, and it's going to give us a new prop. Okay, so that's and. Just to recap, if we have an and in the goal, we can use split, and we'll get two new sub-goals. If we have an and in the assumption, we can use destruct, and we'll get two new assumptions. Okay, we have and. Yes?
And some sort of inductive type then, because we're using destruct, or is it just a coincidence that we're using destruct here?
So the question was, is and a inductive type because we're using destruct just as we did with other inductive types, or is it some weird coincidence? And the answer is, it is no coincidence. They are an inductive type, and we'll look at that definition in more detail tomorrow morning. Okay. Any other questions? Good. Okay, so we have ands. You have ands. What's the complement of and? It's or. As you probably remember from your Boolean logic class or when you did your circuit design. So in coq, of course, we have conjunction for taking the disjunction of two propositions, which is right A or B, as we see here. The definition, wow, yeah, we'll go with that. So, okay, how do we prove statements that have an or in them? How do we work with goals that have or in them? So, oh wait, are we going to use, okay, we're going to look at hypotheses first. Okay, so here's our or example. So what do we do if we have an assumption that is of the form A or B? So here's an example. We know either n equals 0 or m equals 0, and we want to show that n times m equals 0. So if you were doing this by hand, how would you go about proving this?